Lesson 912, the central limit theorem for sample means. Introduction. In Lesson 911, we found random samples of acorn weights from a population of 400 real acorn weights. In this lesson, we will use computer simulations to learn more about the distributions of sample means. Pay special attention to the shape of the population distribution and how the shape of the population distribution compares to the shape of the distribution of sample means for different sample sizes. This lesson uses the online simulation from the Take It Home section of Lesson 911. So if you haven't started that Take It Home yet, if you watch what we're about to do here, this will give you some insight on how to use that simulation for that Take It Home. So I'm going to go to this website, carnegiemathpathways.org/go/samplingdist. So I have it over here. And that brings me to this website, and I'm going to click on Begin under Sampling Distribution on the left. And then I'm going to be following the words in the worksheet as we see things on this website. So first of all, under Try These, sampling from a uniformly distributed population. To begin, we will sample from a population that is uniformly distributed. We will use the online sampling distribution simulation to simulate the creation of 10,000 random samples from this population. We will use 3 different sample sizes. First, we will create a distribution of sample means for 10,000 samples of size 2. Next, we will create a distribution of sample means for 10,000 samples of size 10. And finally, we will create a distribution of sample means for 10,000 samples of size 25. So first, the population distribution is the top graph. Click the drop-down menu labeled Normal and select Uniform to set the population distribution to uniform. Number 1 says, describe the shape of this population distribution. What are all the possible values in this population? If you look at the graph that's at the top of this screen, you can see it just is a rectangle. And that should be what we expect of uniform distribution. So the shape would just be a rectangle. And then what are the possible values in this population? We can notice that on the left of the horizontal axis, we have 0. And on the far right, we have 32. And we have this shaded area above all of those values between 0 and 32. So those are all of the possible values. So back on our worksheet, I would write for number 1, the shape is rectangular. And then the possible values are from 0 to 32. And then number 2 asks, are some of the population values more likely to occur than others? Again, what we need to remember is that shaded areas relate to probability. And as you can see, we have the same height above every single value, which means there's the same area above every single value, which means they all have the exact same probability. If they all have the same probability, then none are more likely than others. So if it says, are some of the population values more likely to occur than others, we would say no. All have the same chance of occurring. All right, turning the page. Step 2, distribution of sample means. Below the population curve is a plot of sample data. To the right of this plot are buttons for selecting the number of samples. Animated is 1 sample, 5 is 5 samples, 10,000 is 10,000 samples, and so on. So going back to our graph here. The first bullet point says, set the sample size n to 2 by using the drop-down menu labeled n equal 5. So that's in the middle of the screen, n equal 5, and I'm going to select 2. And then set the number of samples to 10,000 by clicking the button labeled 10,000. So that's the button below the word sample, and I click that button, and now I get a graph. In the third graph, the distribution of means plot, you will see sample means from 10,000 random samples of size 2. Number 3 asks, what is the range of the sample means in this distribution of sample means? Here again, if we look at the horizontal axis, we see on the far left is 0 and on the far right is 32, and we have values above each of those numbers. So again, we have a range that goes from 0 to 32. So that's what I'll write for number 3, 0 to 32. That would be our max and min, so the minimum is 0 and the maximum is 32. We could also do something that we would have done in Math 21a. If we want to find the range, that's just the maximum minus the minimum, and that's 32. But really what we're trying to focus on here is that the values range from as low as 0 to as high as 32. Number 4 asks, what is the shape of the distribution of sample means? If we go back to our graph, looking at this graph, we see that it is low on the left and the right, and that it reaches its highest values in the middle, the center. So this should remind us of a normal distribution. So maybe we could say approximately bell-shaped. And if we compare it to the original graph that's at the top of that screen, we can definitely see that it is not uniform anymore. Number 5, sketch the distribution of sample means for n equal 2 in the box below. Run the simulation for sample sizes n equal 10 and n equal 25 by using the drop-down menu to first select n equal 10 and then n equal 25. For each simulation, set n equal to 10,000 so that 10,000 random samples are created, and then sketch your results in the boxes below. So for n equal 2, we already have that graph, and it's got a wide distribution, so we'll have something that's approximately bell-shaped and extends to both ends of our box for drawing this picture. And we've got a center that's in the middle. So it could be something like that. Again, you can make your own drawing. That's just approximately what it could look like. Then for sample size n equal 10, we'll select that. We have to again push the button for 10,000. And notice what happened here. We still have approximately bell-shaped, but the distribution is not as wide. You can even, if you try to look at the horizontal axis, you can think that where the smallest value is, it's at about 1, 2, 3, 4, 5, 6, 7, about 7, and the highest value is not as high as 32 anymore. It's maybe 25. So we've got a skinnier distribution. So in our graph for this, we'll just make it skinnier than what it was. And then for n equal 25, again, I'm changing my sample size to 25. I have to click the button 10,000 again to generate the graph. Notice again, this shape is approximately bell-shaped. And again, the distribution is not as wide as what it was for the previous two. So going back to my sketch, just something that's skinnier than what it was before. And really, this is all we're trying to notice, is that the distribution is becoming skinnier as the sample size is increasing, which is something that we've seen before in a few modules. So number 6 asks us to reflect on what we've just noticed. So first of all, what happens to the center of the distribution of sample means when the sample size increases to n equal 25? What happens to the variability of the distribution when the sample size increases to n equal 25? To be a little bit more specific with this, maybe let's use those graphs again and just go back to what we started with, n equal 2. And let's just see where the center is for this. It looks like the center is right in the middle, so halfway between 0 and 32, so 16. Let's then change the sample size to 10 again. And again, you can notice it's right about in the middle, so about 16. And then if we change the sample size to 25, again, we have our center right about in the middle, so at about 16. So what we can say with the center for number 6 is the center stays the same. And then since we've been noticing that the distribution gets skinnier as the sample size increases, that means our standard deviation or our variability is decreasing. So the center stays the same. And the variability decreases. Already we should be reminded of when sample size increases, the variability or the error decreases. And then number 7, identify the mean and standard error of the distribution of sample means when n is equal to 25. How do the mean and standard error of this distribution compare to the mean and standard deviation of the population? If we go back to our graph, we can actually get this information from some of the numbers here. First of all, in the distribution of means graph, the one that we've been changing with different sample sizes, to the left, we can actually see some of the information that they're asking about. The mean says 16.05, and then SD, the standard deviation, is 1.89. So for our first part of this, identify the mean and standard error of the distribution of sample means when n is equal to 25. The mean, again, is 16.05. And the standard error or standard deviation, that is 1.89. How do the mean and standard error of this distribution compare to the mean and standard deviation of the population? If we go back to the population graph, the uniform graph, we can see that the mean there was 16 and the standard deviation was 9.52. So the mean is very close to what it was from the population, but the standard deviation is definitely lower than what it was for the parent population. So the means are about the same. But the standard deviation is lower than what it was for the population. Okay, so to continue, we're going to look at some different distributions. So next, sampling from a population that is not uniformly distributed. Let's sample from a population whose distribution is skewed right and not uniform. Let's simulate 10,000 random samples using 3 different sample sizes, n equal 2, n equal 10, and n equal 25 again. Set the population type to skewed by using the top drop-down menu where we selected uniform before. If you want to make the population distribution more skewed, drag your mouse pointer along the population graph and adjust the shape. Then set the sample size to 2, and then set the number of samples to 10,000 as we've done before. So when I go back to the website, where it says uniform, I can select skewed, And you can notice here that it's skewed right. We've got a right tail, so it's skewed right. But you can change this. If you just use your mouse, you can click and drag, and you can change this shape to whatever you want. So I'm just going to select skewed again, or actually uniform to clear that, and then go back to skewed. And now I have skewed right. So let's see. We need to set our sample size to 2, and then our number of samples to 10,000. And then we have some questions about the distribution of means graph that we just generated. So first, number 8, what is the range of the sample means in the distribution of sample means? So here we can see that it starts on the left at 0, and then let's see if we can count how far up it goes. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, about 23. Just counting from the left to the right. So it looks like our range is from 0 to 23 for number 8. And then if we want to describe the shape of this distribution, we would say that it's skewed right. So for number 8, 0 to 23, and then it is skewed right. We're saying skewed right because we still have a right tail on this distribution of means graph in the center of the screen. So next we're going to do some sketching like we did before. So number 10, sketch the sampling distribution of sample means when n is equal to 2 in the box below. That's the graph that we have up on the screen right now. Run the simulation for sample sizes n equal 10 and n equal 25 by using the drop-down menu to first select n equal 10 and then n equal 25. And then again, for each simulation, we have to click the 10,000 button to get a new graph. So here we can draw the graph that we have for this distribution of means for n equal 2. Let's keep in mind that it's got a wide range from 0 to 23, and that we should expect what we saw happen before. When the sample size increased, the distribution gets skinnier, so we should try to expect that in our next 2 graphs. So my first graph, something like that. Now let's go back to our website, change the sample size to 10, generate our graph again. Notice what happened. We definitely got a skinnier distribution. But also think about the shape of this. It still might be a little bit skewed right. There is a slight tail, but it is starting to look approximately bell-shaped. So we'll keep that in mind with our sketch. And then finally for sample size 25. Notice the distribution got skinnier again. It definitely looks more bell-shaped now, so that's going to influence our graph. But more importantly than just drawing these sketches, let's look at number 11. Number 11 says, what happens to the center of the distribution of sample means when the sample size increases to n equal 25? What happens to the variability of the distribution when the sample size increases to 25? So again, we noticed that the graphs were getting skinnier in their distribution. So we already know that the variability is decreasing. But let's try to focus on the center. And to help us with this, let's remember there's some numbers to the left of these graphs that we can actually focus on. So notice that the first graph that we have when the sample size is n equal 2, we've got this wide distribution. And if you want to find the center, you could look at the horizontal axis. And it looks like it might be around 1, 2, 3, 4, 5, 6, 7, 8, or 9. But to also help us with this, take a look at the numbers on the left where it says mean is 8.15. So then when I change the sample size to n equal 10, again, look at the mean that's written down on the left. it says mean is equal to 8.12. So it's still staying around 8. And then for sample size 25, the mean says 8.08. So again, the mean is still staying around 8. So we can say that for number 11, the center stayed about the same and the variability decreased. Number 12, identify the mean and standard error of the distribution of sample means when n is equal to 25. How do the mean and standard error of this distribution compare to the mean and standard deviation of the population? So first of all, we just left off with the mean was 8.08. And let's go back to our graph and see how that compares. First of all, notice that the mean for our parent population up at the top of the screen says 8.08, and the mean that we have for our distribution of means, that's also 8.08. So the mean is the same. And then our standard deviation for the distribution of means, SD, equals 1.23. That's smaller than the standard deviation, 6.22, that was there for the parent population. So the mean stayed the same. Our standard deviation with our distribution of means is 1.23, and that's smaller than what it was for the parent population. All right, continuing, sampling from any population. We will now sample from a population with an even more unusual distribution. Try to create a population distribution that is so unusual that even when we increase the sample size, the distribution of sample means will not become bell-shaped. We will again simulate 10,000 random samples using 3 different sample sizes. So if you think about what this is asking, we've already seen a couple of distributions. One was skewed, one was uniform, but we ended up getting a normal distribution as we got to sample size 25. So we're going to select custom, and then we're going to draw our own parent population. So I'm going to do something that is intentionally not bell-shaped. So I'm actually going to do something that has a few different peaks, maybe separated like that, where I've just got these 4 almost little building shapes that have peaks on them. And I'm going to set my sample size to 2, as they say, and then my number of samples to 10,000. And number 13 asks, sketch your population distribution in the box below. So that's the top graph with the 4 building shapes that I have there. So I'm going to go back to number 13 and sketch that in there. So I've got something that looks like this, like 4 columns. Number 14 asks, what is the range of the sample means in the distribution of sample means? Here I've got values all the way as far to the left as 0, and then values up as high as 32. So my range is 0 to 32. Number 15 asks, what is the shape of the distribution of sample means? Can't really identify a shape from this, since it looks like I've got 1, 2, 3, 4, 5, 6, 7 little peaks, or 7 buildings that came from the 4 buildings. So our range for number 14, 0 to 32. And then number 15, what is the shape? You can describe that shape however you want. We don't really have a word for that. So how about unknown? Number 16, sketch the distribution of sample means when n is equal to 2 in the box below. I had 7 little building shapes, so that was something sort of low on the left, and then it started to get to some high building shapes in the middle and then low again on the right. Maybe that's reminding us of something. And then let's do the same thing for n equal to 10. All right, looks like we've got something approximately bell-shaped. The distribution is not as wide from 0 to 32 as what we had in the previous graph. What happens when we go to 25? Even more so, approximately bell-shaped, and it's a skinnier distribution. So then number 17, what happens to the center and variability of the distribution of sample means when the sample size increases to 25? Maybe think of what we've already said with that same question in the previous examples that we've looked at. But if I go back to my graph, we can also just look at the mean for each. For sample size n equal 2, the mean is 14.23. For sample size n equal 10, the mean is 14.16. For sample size n equal 25, the mean is 14.15. All of those are around 14, and the distributions got skinnier, so the variability is decreasing. So the center stayed the same for number 17, and the variability decreased. Number 18, identify the mean and standard error of the distribution of sample means when n is equal to 25. And then how do the mean and standard error of this distribution compare to the mean and standard deviation of the population? So going back to our graph, the mean we have is 14.15. That's the same as what it is for the population up above. And the standard deviation is 2.03, and that is smaller than what it was for the population. So 14.15 for the mean and 2.03 for the standard deviation. And the means are the same or equal. And the standard deviation is smaller than the population standard deviation. So finally, after all of these different distribution shapes, what if we sample from a normal population? For the last example, we will sample from a normal population. We're going to set the population type to normal. Again, set the sample size to 2 by selecting n equal 2, and then set the number of samples to 10,000 by clicking the button labeled 10,000. And then we'll ask a couple of questions. So going back to our graphs, we'll set our population to normal, our sample size to 2, and then click on 10,000. And then again, we can also click on n equal 10, 10,000, and then n equal 25, clicking on 10,000. And what we're seeing here shouldn't be very surprising. So first of all, number 19, does the distribution of sample means appear normal? Again, if we just go back to n equal 2, we would definitely say yes, it appears to be approximately normal for number 19. And then also number 20, experiment with different values of n up to 25 using the drop-down menu. Be sure to click the 10,000 button to collect 10,000 samples each time that you change the sample size. are you able to construct any distribution of sample means that does not appear normal for any sample size? As we already saw, n equal 10. We can even use n equals 16 that is here. N equal 20. All of the graphs that we're getting are bell-shaped. So the answer for number 20 would just be no. We can't construct anything that doesn't appear normal. And then finally, number 21. When sampling from a normal population, is any restriction upon sample size necessary in order for the distribution of sample means to be normal? No. We saw with n equal 2, we had a normal distribution, and n equal 25, we had a normal distribution that came about in the distribution of sample means. So it didn't matter what the sample size was. So everything that we've seen in all these examples is now summarized here in this you need to know box. The central limit theorem for sample means states that given any population with mean mu and standard deviation sigma, the sampling distribution of sample means sampled with replacement from random samples of size n will have a distribution that approaches normality with increasing sample size. The mean and standard error of the sampling distribution are given below. Mu sub x bar is equal to mu. So first of all, if we just want to interpret those symbols, mu sub x bar, that is the mean of sample means. Maybe think back to module 7, where we had the mean of sample proportions. And then we have is equal to mu on the right, that is just the symbol for population mean. And then the next equation that we have, sigma sub x bar, that means the standard deviation of sample means. And that's equal to sigma divided by the square root of n. Remember that sigma is the population standard deviation, and n stands for sample size. So random samples of size n, standard deviation for the population sigma, and mean mu. The criteria for the approximate normality of a sampling distribution are that either the population from which we are sampling is normal, because as we just saw, if it's normal, then we always will get a normal distribution in our distribution of sample means, or the sample size is greater than 30. Very non-normal populations may require samples substantially larger than 30. So then to finish, next steps. We will now shift our attention from the distribution of sample means to the sampling distribution of sample means. The sampling distribution of sample means is the distribution of all possible sample means from random samples of the same size. When a sampling distribution of sample means is approximately normal, we can use its mean and standard error to find the z-score of any particular sample mean. The z-score of a sample mean, x bar, from a sample of size n is found by the formula z equal x bar minus mu divided by this fraction, sigma divided by the square root of n. Notice again this z-score is very similar to what we saw with Module 7 and Module 8. We have sample information, that's x bar, minus population information, that's the population mean, mu, and then divided by the standard deviation, sigma divided by the square root of n this time. In the previous lesson, we explored a population distribution of acorn weights from oak trees. We saw that acorn weights are normally distributed with a mean weight of 3.75 grams and a standard deviation of 1.02 grams. The population of acorn weights is displayed in the graph below. Population of acorn weights, we have this horizontal axis going from as far as negative 0.25 on the left and up to 7.75 on the right. And it looks like the center is somewhere in the middle, about 3.75. By the way, our secret word now for this lesson is going to be grams. Grams, grams. That's our secret word. So suppose that we randomly select samples of 40 acorn weights. According to the central limit theorem, since the population is normally distributed, sample means from random samples of size 40 will also be normally distributed. Number 22, the sample size is n equal 40. Use the central limit theorem to calculate the mean and standard error of the sampling distribution. So first of all, mu sub x bar, the mean of sample means, is equal to the population mean. The mean was 3.75 in the paragraph above. And then for sigma sub x bar, that's equal to the population standard deviation sigma, which we were given as 1.02. And then we have to divide that by the square root of the sample size, which is 40. So I would suggest find the square root of 40 first. And you can write that down separately, or if you're using a graphing calculator, you can put this all in at once. 1.02 divided by the square root of 40. And if we round to 3 decimal places, we get approximately 0.161. Number 23, a particular random sample of size 40 has a mean weight of 5 grams. Find the z-score for the sample mean x bar equal to 5. So here, z is equal to x bar minus mu divided by sigma divided by the square root of n. We already have all of these numbers. X bar was just given to us as 5. Mu up above in number 22 is 3.75. And then divided by our standard deviation, which we just found, 0.161. So first 5 minus 3.75. And then we're going to divide that by 0.161. And we get approximately, again, rounding to 3 decimal places if we want, 7.764. So then finally, number 24, would you consider this sample mean to be unusual? Be sure to explain your answer. So let's think about what we've seen with z-scores. Usual z-scores are those that are within 2 standard deviations of the mean, meaning z-scores as low as -2 and as high as +2. Those are usual. This z-score that we just got in number 23 is higher than 2. So it is outside of that usual range. So we would say, yes, it is unusual because it is not between -2 and 2.